Alright, so welcome back to another video on this course. So next up, we're going to be talking about the area under the curve, or specifically under the receiver operating characteristics curve, the ROC curve. You know, it is actually one of the most popular, uh, commonly used performance measurement for classification problems at various thresholds, right? So the ROC itself is a probability curve, right? And the area AUC, the area under the curve, represents the degree of or measure of separability. The higher the AUC, the better the model at the better the model is at predicting classes as zeros and zero classes as zeros and one classes as ones. And by analogy, the higher the AUC, the better the model at distinguishing between, like, let's say, patients with the disease and patients with no disease, right? And something we have to know is that the ROC curve is plotted with the true positive rate against the false positive rate, where the true positive rate is on the y-axis and the false positive rate is on the x-axis. Okay, so in order, so a really important concept for the AUC or ROC, or sometimes it is called AUROC, um, area under the receiver operating characteristics. Uh, the most important terms are true positive rate and false positive rate. So true positive rate is essentially the same as recall. So if you can recall, yeah, uh, it's actually true positive over true positive plus false negative, right? So um, we would like to actually find something that is that can capture as many positives, as many true results as possible, like actual positives are correctly classified, right? And to try to and now if we want to um, find how to calculate false positive rate, first we have to understand about specificity, which is true negative over true negative plus false positive, right? So it's like the other way around. When we're talking about sensitivity and specificity, right? And the FPR, the false positive rate score, is just 1 minus 1 subtracted by specificity, or essentially you can say false positive over true negative divided by over true negative plus false positive, right? Okay, so how to essentially speculate, right, about the performance of the model. So an excellent model uh, has AUC near 1, near the value of 1, which means it has a good measure of separability. A poor model has an AUC near the value of 0, which means it has the worst measure of separability, right? Yeah. Okay, so it means it is actually okay. Technically, if you have an AUC model, an AUC score nearing 0, it means the model is actually reciprocating the result, right? Like it predicts like zeros as ones and ones as zeros, negatives as positives and positives as negatives. It's like the other way around, and when the AUC is like 0.5, it's like in metal, it means that the model has no class separation or capacity whatsoever. Okay. Okay. All right. So, um, okay. So perhaps I'll talk a bit about, like, before we jump in to uh, why it's desirable and why it's not desirable, right? We perhaps can talk about sensitivity and specificity, right? and the threshold itself. So sensitivity and specificity are inversely proportional to each other. So when we increase sensitivity, specificity decreases, and vice versa. Uh, when we decrease the threshold, we get more positive values, right? And um, thus, like assuming that everything above the threshold is considered positive, right? So uh, it increases sensitivity and decreasing specificity, right? And similarly, if we increase the threshold, that means more values are located are less than the threshold rate, which means we get more negative values, and um, you know um, we get higher specificity and lower sensitivity, right? And since we know that FPR, or the false positive rate, is 1 subtracted by specificity, that means when we increase the true positive rate, the false positive rate also increases. So yeah, it's actually proportional to each other. Okay, so I suppose let's talk about why AUC is desirable. It is actually desirable for two reasons. The first one is that it is actually scale invariant. So um, this scale invariance property is essentially the property of having the same value for an evaluation metric when the rank order remains the same, right? So like yeah, yeah, it measures really well. It measures how well the predictions are ranked, right, rather than absolute values, right? So it's actually invariant towards the scale and stuff. And the second reason is that it is actually threshold invariant. So classification threshold invariance means that let's say uh, it's actually like, for example, because we demonstrated before that like it doesn't like it does measure like threshold in every single value out there, right? Like it takes into account the threshold as well, like in every single value. So it's not dependent on a certain value of threshold, essentially. And that's why we want the the metric to be, yeah. And I think this is desirable because a lot of time we want a metric, a performance metric that is threshold invariant, right? But it does come with a caveat, in that scale invariance is not always desirable, because sometimes we really do need well calibrated probability outputs, right? And the AUC doesn't tell us that. And the second reason is that the threshold invariance is actually not always desirable, because sometimes there are wide disparities in the cost of false negatives versus false positives, and it may be critical to minimize one over the other, right? And like, for example, when doing spam email spam detection, you might wanna prioritize minimizing false positives, right? Like tagging um, spam, a supposedly not non-spam email as spam, right? It's very fatal because the person wouldn't actually get the email, right? Rather than the other way around, the false negative, you know. So yeah, AUC isn't actually this useful for this metric. This metric is actually not that useful in that situation. Yeah. Okay, so we talked about AUROC, right? And um, essentially, what I've been talking about so far, accuracy, position, recall, F1 score, AUROC, are the five most common ways of actually, you know, trying to measure how well a model performs, right? But I decided to add like fitting time as well as scoring time. So essentially, model fitting is a measure of how well a machine learning model generalizes to similar data to similar data to that on which it was trained, right? And essentially, model scoring is the process of applying an algorithmic model built from a historical data set to a new data set to uncover insights, right? Help a business help solve a business problem, or like other contexts, other possible contexts. It's just like in business settings, right? Like for example, I've done COVID-19 pandemic stuff as well. So yeah, and essentially, fitting time and starting time are just the time it takes for uh, you know for us to like do a model fitting with that particular model, right? And scoring time as well. Do model scoring with that specific um, model. Okay, so why does it matter? It matters because it has something to do with computational power, something that not a lot of people may have. Like um, in a business setting or like a research setting where we get a lot of funding, it is actually very easy for us to get like enough hardware, like proper hardware to do data science work, right? But that's not always the case, right? Like for example, I'm currently right now using a laptop, and obviously I can't do like very intensive work, right? And therefore, it is actually perhaps for those people who have like limited computational power, it is actually uh, possibly um, preferable um, to use a fitting time or a scoring time that is fast, as compared to like the most accurate one, because yeah, it's gonna take a long time. This case is very rare because this case practically means like you don't have like enough time, let's say, to complete the you know model fitting and model scoring in time, right? Essentially, like in any case, in most cases, in you would want to have like the best like performing model, right? But it's rarely the case. It's practically possibly never, because like in any case, like you want to have like the best model. But yeah, I suppose this is something that people may consider although it's not very important. So I will, in my analysis later on, in my discussion results and discussion, like I will not be focusing on those two that much. But yeah, I just um, put it there for those who may find it useful, I suppose. So yeah, I suppose that's it for this video, and I'll see you in the next one.